Hello, I'm David. I'm the coordinator of the Maths Learning Centre. This is a revision seminar for Real Analysis 2 in Semester 2, 2020, which is why I'm in my house instead of in a lecture theatre. I've got a couple of requests from someone, and I'm going to talk them through on the document camera. So what I've been asked about is openness and closedness. And proving that sets are open and or closed, and how to do that. And I've asked my friend here to remind me what the lecturer says the definition is. And he says the definition is this: U is open when for all A in U there is an epsilon greater than 0 such that the interval A minus epsilon to A plus epsilon is contained in or equal to U, or just contained in. That's the definition of open, and the definition of closed when R without U is open. Wesley, can you confirm, like with a thumbs up or something in the chat, that I've got that right? Cool. Okay. So I like to think of open being about what happens on the inside of the set and closed being about what happens on the outside of the set, because it's about the complement. And my picture understanding of how open and closed works is something like, there's the number line, and here's my set U, and no matter which point within that set I pick, like this point here, for example, then it's possible to have an open interval centered on that point, and I can make it small enough to fit inside the set. And it doesn't matter how close to the edge, pardon me, of the set I am, I can always make my find an open interval that's small enough. So if I had like a magnifying glass to zoom into this bit just here, and here's the set coming in here, then even if I was very, very small, close to the edge of the set, I could still find an open interval that was small enough to fit inside the set after all. That's my understanding of what open means. And closed is the same, except that you're thinking about points that are on the outside of the set. So closed means at any point that you pick outside the set, you can find a closed interval, an open interval that's small enough to be completely outside the set. And it doesn't have to be one continuous line like this. It can have holes in it and all sorts of interesting things going on. And that's when it becomes hard to tell that it's open or closed. Okay. Right. So in my head, I'm imagining making things smaller until it fits inside. So there's a couple of other things that are useful to know about how this works, is that in a proof, we have to use mechanisms that go with proofs, and we can't just draw pictures, but the pictures can help us to figure out what the proof is. So if you go back to this definition, U is open when for all our numbers A in U, there is an epsilon greater than 0 such that this interval is contained in U. I've got a few things that I'm going to need to talk about there. One thing is how to show that an interval is contained inside a set. So this interval is a set of its own. And so to show that one set is contained in another, you would need to show that anything that is in this interval is also inside U. And so to show that working would normally go that you would pick something that's in this set, and then you would do some sort of working, and you would conclude at the end that therefore B is also in U. And so you say, well, if there is a number, any number that you can think of in here, blah, 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 therefore that number's in U as well, that means that the entire set is inside U. And there just has to be something in this position here. Okay, that's how to prove that this part of the proof, that very end bit, that's how to do it. And the issue is that we're going to need to know what to do in this space here. But at any stage where you're not sure what to do, you can ask, what does it mean to write down the thing that I wrote down? So this thing here that I wrote down, what does it mean for B to be in this set? Well, it means that B is between A minus epsilon and A plus epsilon. Excuse me, I'm just going to scam phone call. Okay, so can I just check how you're feeling about what I've said so far? Cool. All right. So this means that B has to be between this number and this number, because that's what an interval means. And that also means that there are several different ways of dealing with that, and you don't have to write them all in your proof. But for B to be in this set, in fact, I'm not going to write it in this spot here. I'm just going to write it on another piece of paper. For B to be in that set, I'll just draw a picture of it. There's A, that distance is epsilon, that distance is epsilon. And so this is the set here from A minus epsilon to A plus epsilon, and B is in there somewhere. Okay, it's going to fix my focus. No, unfixable. Okay, for to be in that set, it's somewhere between A minus epsilon, whoop, strictly less than, and A plus epsilon. And if I subtract A from everything, that means that it's between B minus A is between there and there. And if I did the absolute value on anything, that would be to say that the absolute value of B minus A has to be less than epsilon, because the number is between minus epsilon and plus epsilon. So in your absolute value, it'll be between 0 and epsilon. So these are all equivalent, these statements. They mean the same thing. And from the picture point of view, this literal thing here says the distance between B and A is less than epsilon. Because when you do the absolute value of two things subtracted, it's the distance between them. And that makes sense from the picture, because that's saying that if B is in this set, the gap between B and A is less than size epsilon. So if B is on this side, it's less than epsilon. If B is on this side, it's less than epsilon. And this is probably the most useful way of thinking about it in order to construct proofs. We need to make, knowing that B is in this set means that it's very close to A. So an alternative way of writing the definition would be to say, there is an epsilon such that, so we could change the definition here to say instead, such that for all B with the distance between B and A less than epsilon, B is in U. So that's an alternative way of writing the definition. The reason I like this way of writing the definition is it feels like it matches with the definition of things like continuity a little better, but it's just good to know that it's there. If your lecturer's definition is this, then that's all right. You just have to know that it means the same thing. Okay, so that's cool. Where's my proof gone? So we know what to do with this bit here. There's various different things we can turn that into. Any one of those will do. And at this end, the only way we're going to be able to conclude that B is in U is to somehow, in this position just before that, say that B satisfies the rule for being in U. So the only way we're going to be able to conclude that B is in U is to go and look to see what the rule is for being in U, and then it show that the number B has to satisfy that rule. Okay, so this hopefully will all make more sense when I actually do a problem. And I've been asked to talk about showing that R without Z is open. So if I'm going to use the definition to do that, then I'm going to remember that the definition goes U is open when for all A in U there is an epsilon greater than 0 such that this. And any proof that I've only talked about this part of the proof, but any proof that runs like this is going to begin, it says for all A, it's going to begin with let A. In fact, I'm just going to, yeah. So my proof is going to go something like this. Let A be in R without Z, because my definition begins with a for all A. And then I'm going to have to tell the reader what epsilon is. It says there is an epsilon, so I have to somehow convince them that the epsilon exists. And usually the quickest way of doing that is to tell them what the epsilon is. Excuse me. And then I need to argue that for every B in this interval, it's contained in U. So somewhere along the lines, I have to tell them what epsilon is. And so this bit here has to be what is epsilon. And then I have to say let B be in this interval. And then I have to do some working and conclude that B is in U, let's call it U. All right, that's the plan for my proof. Of some sort. That's what the proof of something being open is going to look like. And all proofs of things are open are going to look like that. The trick is figuring out what epsilon has to be. So now, before I come up with my proof, I'm going to draw a picture. Okay. So let me draw a number line. Oop, I've lost my... and U is the whole of R without Z. Okay, so that would mean that this is everything. And these are my Zs. And my set doesn't have any of these points, but it's got everything in between. Okay. So if I did pick a random point in here somewhere, and I need to imagine making an interval centered on A as small as possible until it fits completely inside this set. If my interval's too wide, it'll go past one of these empty holes and it won't be inside the set fully. So my interval's going to have to fit inside this gap here. So it seems to me I'm going to need to choose my epsilon to be smaller than the distance between A and the nearest integer. That's what I'm going to need to do. Okay, that looks like my plan. Epsilon's going to have to be that. And so, all right. So if A is close to an integer from below, that might be a bit tricky. We need to figure out a way of writing that down. That's the next step. Hey, we've just got a new person, just letting you know. We're recording at the moment, and we're talking about open and closed sets right now for real analysis. And we're in the middle of trying to prove that R without Z is open. And we've drawn a little diagram of R without Z. We've said what would happen if we picked a number, and our interval would have to, we need an interval small enough to fit completely inside this set, which means it's not allowed to hit any of those empty holes. So, yeah. So the epsilon that we pick has to be smaller than the distance between A and the nearest integer. So I'm thinking that now I'm going to do my proof. Let A be in R without Z. Okay. Then A isn't an integer, which is a good point. And so therefore A is going to be between two integers, because that's how the integers work. Okay, so A is between two integers. So let n in Z, I should give those integers names. So let n in Z be such that n is less than A, which is less than n plus 1. Okay, so you can always find something that's an integer that's close to A. I guess that's to do with the, there's a word for it, but basically a set of integers that's bounded above has a maximum. That's a rule for integers, I'm pretty sure. Wouldn't know what it's called. You'd have to look that up in your notes. Okay, so this is me trying to get a handle on this picture. So this is my n here, and this is n plus 1. And then I want epsilon to be the shortest distance between A and those things. So I'm going to say that that epsilon is equal to, it might be easier to let people know that I'm going to choose this. And n isn't just any integer, so we're going to say, no, I'm just going to leave that. So we're going to choose my epsilon to be the distance between, the smaller of the two distance between A and N and between A and N plus 1. And A minus N is good because the N is less than A. That's a nice positive number. And an N plus 1 minus A is positive 2. So that's good. So epsilon is positive. And so that's now this distance here, this epsilon here. And now I have to show that anything that's less than that away from A has to be not an integer, basically, because that's the rule for being in this set. Being in this set means being a real number, but not being an integer. So, cool. Let B be in this set. Okay, so that means that B is between like that. All right. And so let's see. So now B is greater than A minus okay, so we need to show that it's not an integer. I mean, we know what's going on here, actually. We've chosen B specifically so that it's in this space here. So the B is going to hopefully be guaranteed to be less than n plus 1. So if we can show that B is less than n plus 1 and more than n, it can't be an integer because it's between two consecutive integers. So why don't we go B is less than A plus epsilon. And this is less than both of these numbers. So if I choose this one and put it in instead of epsilon, that'll make the a's disappear. So that's less than or equal to a plus n plus 1 minus a, because epsilon is the minimum of these two numbers. And that's equal to n plus 1. So therefore, b is less than n plus 1. So we now need to convince ourselves that b is more than n. Okay. Also, epsilon is greater than is. My problem at the moment is that I'm worried because I need a greater than. And my knowledge about epsilon is it's less than stuff. Oh, but it's a minus epsilon. If epsilon's less than something, then minus epsilon is going to be greater than something. Okay, got it. Okay, so we know that epsilon is greater than a minus n, which means that minus epsilon is less than n minus a, because it just times everything by minus 1. So therefore, now b is greater than a minus epsilon, which is, oh no, damn, e was less than or equal to this, wasn't it? Because it's the minimum. Oh, I always get my less than or equal to's round the wrong way and have to concentrate. But at least I knew what I was aiming for, which allowed me to check that this was round the wrong way. Right. Let me just check about this. There's n, there's a. Epsilon is smaller than this, which means that minus epsilon, which is all the way over here, okay, cool. All good, I'm happy. So a minus epsilon, which is greater than or equal to a plus n minus a, which is n, so therefore b is greater than n. So n is less than b, which is less than n plus 1, so b is not an integer. And therefore, b is in the real numbers without z. And so the real numbers without z is closed. How do you feel about that, or any of that? Don't know if I can fit it all on the same screen at once. Now, how do you feel about trying to do that again in, say, an exam? All right. Yeah, it can be very confusing. And I think one of the things that I'm going to ask you in a minute what you think is confusing, but other people say that one of the things that's confusing, you understand what the thought process is? Yeah. One of the things that's confusing is that every situation is going to be a little bit different, that the decision about how to do the different parts of what happens there is going to be different every time. We had to do some fairly fancy reasoning and define some other numbers, letters that were particular numbers, in order for us to even come up, describe what it was we were thinking about what the epsilon had to be. And that's often a tricky part to say, okay, I can see in my head where the distance is that I need to think about. How am I going to describe to someone what that is using maths notation? So that one's a bit tricky. This took us a little bit of thinking based on a diagram. And then the next decision is going to be a little different depending on your definition of epsilon and how you're going to do the working. But it's often going to be inequality reasoning, where you're allowed to move forward with less thans and or equal tos and that sort of thing. Would you like to? Yeah, we just showed that R without Z is actually open. Oh crap, closed, it's open. Open. Thank you for pointing that out. We just showed it's open. It was hard because I kept thinking it was closed because we kept saying not. So we've showed that Z is closed. Maybe that's what I was thinking. So yeah, it's probably worthwhile. All right, let me just have a look. That's another thing I have trouble with. Just got to, for everyone who's watching this, I'm reading the chat here. So another thing I have trouble with in general, negating definitions and when we're asked to show if something is not open or not closed, and because open and closed are not opposites of each other. Yeah. Okay. So if we want to show that something's not open, that's not the same as showing that it's closed. And that's something that's confusing to you. Do I understand what you mean there, that's part of what's causing the confusion? Okay, so we should find a set that isn't open and show that it's not open. That might be a good example to run through. Show that the interval from 5 to 7, including 5 but not including 7, is not open. Now I know it's not open because this end goes all the way up to 5. So we wouldn't call them open intervals if there were other intervals that were open. So, but that's just a convenient thing that the maths terminology matches up with our intuition. Yeah. So let me have a look at the definition of being open again and see what happens when it's not there. Where'd it go? Whoops, not my document camera. That was a very good question, by the way. Get my definition. Oh, it's all the way over here. Okay. So to be not open, I'm just gonna be not open, then I'm just gonna focus on this definition one piece at a time. I know there's rules for negating things that have for alls and such stats, but I'm just interested in having a look here. So it starts off with U is open when for all A and U, this thing here happens. There's a thing here that happens, but I don't want to focus on that at the moment. So U would be not open if not for all the U's this happens. So just a second. U is not open so not all the A's in U, this thing here happens. Okay, so that would mean I'm going to write lots of different versions of this. U is not open when at least one A in U, this doesn't happen. That's how I negate it. And I mean, it's important to not try and do this on the fly, but I have to keep doing it all the time. So it's not open when for at least one A in U, this thing here doesn't happen. Okay, so that's the difference when something's defined as happening, defined by saying that something happens all the time. Then the opposite of that is that sometimes the thing doesn't happen. It only has to not happen once, and then it's not open. Okay. So that would mean that if I want to show that something's not open, I have to find a specific number in the set that will make it, that will make this thing not true. Okay. And what is this thing? This thing, excuse me. This thing was about being able to find that very small open interval that contains your point. So that would mean if I had at least one point where that didn't happen, then no matter how small I made my interval, it would have to always be not contained in U. So let me just come closer to this thing. What does not this mean? So this says there is an epsilon such that this is contained in U. If that's not true, then that means there's no epsilon such that this is contained in U. So U is not open when there is at least one A in U. Such that there is no epsilon greater than 0 with this thing contained in epsilon, contained in U. And for there to be no epsilon that does this would mean to say that no matter which epsilon we pick, this is always not contained in U. Such that for all the epsilons greater than 0, A minus epsilon, A plus epsilon is not in U. No, not contained in or equal to U. So we're getting closer and closer, but the picture is still in my head. The picture is still in my head that if your set isn't open, then somewhere in your set there is a point such that no matter how close I get to it, the interval is always not contained in the set. And to be not contained in, that would mean there would have to be something in that set that isn't in U, because then it can't be contained in U. So that's our final layer. So that's saying U is not open. Oh, crap. When there is at least one A in U such that for all epsilon greater than 0, there is a B in A minus epsilon, A plus epsilon, with B not in U. So if there is a B in U that's not, if there's a B in this set that's not in U, then that means that this whole set is not contained in U. And if there is an epsilon such that this, and if for every epsilon there is, this set isn't contained in U, that means that for no epsilons is that set contained in U, which means that there is an A that has no epsilons that do this, which means that it's not for all the epsilons that it does that, which means it's not open. How do you feel about that process there? Still, even though I've done all the logical things to create this alternative definition, it's still in my head that to be not open, there has to be a point basically right on the edge, so that no matter how close you get, there's always got a piece that's outside the set. That's sort of what I'm thinking of. So let's just actually add to it. We've got this definition now. All right. Okay. I'm just going to pop that there. That one's done. I'm just going to sort my crap here and go back to the problem I was trying to solve. Okay. So show that that is not open. When I think about this set, it looks like this. There's 5 and there's 7, and my set goes from 5 to 7. Now, no matter how close to 7 I am, if I'm not at 7, I can always fit an interval small enough inside that. So the only point that's going to be a problem is that point right there. No matter how close, small an interval I pick that's centered on 5, it's always going to have a bit that's less than 5. And that bit that's less than 5 isn't in the set. And so that's going to be my argument. But the proof will run according to that reverse definition of open. So I'm going to convince them that there is at least one A in U where this thing doesn't happen. And that A I'm going to pick is the number 5. Consider the number 5, which is in that set. Okay, so I'm going to say this is going to be the one. So think about it, and I'll convince you that this works. And then I need to convince them that no matter how close I get, it's always got a bit outside. So I'm going to say let epsilon be greater than 0, because I want to say this is going to work no matter which epsilon I pick. And then I'm going to consider the set, the interval centered on 5 with radius epsilon. So this interval, 5 minus epsilon, 5 plus epsilon. And we're just probably don't have to tell people to think about that. We're just going to say let B, no we're not, we're just going to consider that. Consider that. Yep. Okay, so we're going to think about that set, and I'm just going to draw it on my diagram. It's just here. It's got epsilon one way and epsilon the other. And I know that all of these points are actually outside my interval. And so I just need to convince someone that a point out there really exists that isn't in the interval. And I reckon if I go halfway of epsilon down, then it's definitely going to be both inside this interval and outside that set. So that consider goes there. Let B be equal to 5 minus epsilon on 2. So I have to convince them that is in this set. Now let's see. Now, epsilon on 2 is less than epsilon, so therefore minus epsilon on 2 is greater than minus epsilon, and so therefore B minus epsilon on 2 is greater than B minus epsilon. Okay. But also B is less than 5. B is B is 5 minus epsilon on 2, which is less than 5, which is less than 5 plus epsilon. And so therefore B is between, That's a 5 there. I'm getting myself all confused. 5 minus epsilon on 2 is greater than 5 minus epsilon, and so therefore B is greater than 5 minus epsilon because that's what B is. Right. So therefore B is between 5 minus epsilon and 5 plus epsilon. So therefore B is in this set. Doing well. And now I just have to convince them that it's also outside this interval. But B is less than 5. And so B is not in this set. And so therefore 5 minus epsilon, 5 plus epsilon is not contained in 5, 7. And so there is an A such that no matter which epsilon I pick, so there is an A there, such that no matter which epsilon I pick, there is a point in this interval. No matter which epsilon I pick, this interval is not contained in the set, and so therefore this set is not open. Right. Tell me how you feel about that. Good. I'll let you know when the recording is ready so you can watch it again if you need to think it through. So we could also show that this set isn't closed too. Yeah, you're welcome. Negating the definition makes it much easier and clearer. Did you want me to do one about it being not closed as well? Okay, I can do that. So we'll come back to this same question. Now, the definition of closed was I'm just checking to see if other people are trying to get in and can't get in. No, it's all good. The definition of closed is when the outside of the interval is open. So to be not closed, that would be the outside of the interval is not open. I actually find this definition of closed really difficult to cope with, and it's much easier for me to have this definition of closed. So we know the definition of closed is when the outside of the set is open. So what that means, when U is closed, that means that for all A which are in the outside of U, so all A that are in R without U, so all A that are in the outside of U, there is an epsilon greater than 0 such that the interval between the interval of radius epsilon around A is completely contained in the outside of U. So, I mean, the definition is like this. That's being closed. For all A in the outside, there is an epsilon greater than 0 such that that interval is completely contained in the outside. Yeah. And if you actually remove the reference to this set here, and you know, if you know, we talked about this set being completely outside U means that everything that's in this set is outside there. That can make it even easier for me. U is closed when for all A not that are in the outside of U, so not in U, there is an epsilon greater than 0 such that for all b in this interval, b is outside U. Yeah. And this matches in my head with the idea of being closed. If it's closed, you're stuck outside it. Yeah, because the door's closed. It's pretty stupid, but that's just sort of how I think about it. So yeah, the difference between closed and open is that for open, this is an in U and an in U, whereas for closed, this is a not in U and a not in U. Yeah. Okay, so if we're going to show that the interval 5, 7, which is closed at one end and open at the other, is closed, then we can run through this reasoning. Is not closed, then we can do the opposite of this reasoning. So the opposite of this reasoning says that for not every A that's outside U, there is no so for some A that's outside U, there's no epsilon that does this, which is the same as saying for some A that's outside U, all the epsilons inside do not this, which means that for some A outside U, all the epsilons find a B in here that's in U. Right. So the opposite of this is there is an A that's outside U, such that for all epsilon greater than 0, there is a B in A minus epsilon, A plus epsilon, with B in U. So what I've done is I've neatly negated each piece of this. I know that's a rule that you can just do. For alls become there is's, and there is's become for alls, and then we eventually get down to a statement that you can just negate. But I still have to do it one step at a time because I don't trust myself. So that's what we're going to have to do to show that 5, 7 is not open, not closed. So okay, so to be not closed, there would have to be something that's outside the set. I'll just draw a picture of it again. Something that's outside the set, such that no matter how small an interval I put around it, it'll always contain a piece that's inside the set. So if I pick something here, no matter how close to the 5 I get, I'm always going to be able to fit an interval outside the set. If I put something here, no matter how close to the 7 I get, I'm always going to be able to fit something outside the set. But the 7 itself isn't part of the set, and no matter how small an interval I pick around that, it's always going to have a piece that's inside the set. So that's going to cause it to not be closed. So let's see. Consider 7, which is not in 5, 7. So I've made a start on this, and then I'm going to let epsilon be greater than 0, and then I'm going to consider this interval. Okay. And so A minus, no, not A, 7, right? The number is 7, isn't it? So the space between 7 minus epsilon and 7 has to have something in it, and I can call that B. Oh, that's a different way of doing it. That's a better proof than the one I gave last time. Yeah, I don't even have to mention the minus epsilon on 2 if I don't want to. Like it's an interval of non-zero width. Oh, good. I'm glad you can see it now. I'm going to finish it for the benefit of people who are watching, if that's okay. So since 7 minus epsilon is strictly less than 7, there is a b with b between them, because that's how real numbers work. And then b is in this interval. And b oh crap. No, we're just going to have to make sure our epsilon no, I'm going to have to no, I am going to have to be more specific actually. Because if my epsilon was like 3, then I could choose a b all the way down here. So I need to make sure my epsilon's small enough to make my, I'm going to have to just pick it perfectly. So let b be like the maximum of 5 and 7 minus epsilon. So then it's like I'll go down epsilon on 2, go down epsilon on 2, but if I've already gone past the 5, I'll just stick with the 5. All right. Then b is less than 7 minus epsilon on 2, which is less than epsilon. No, other way around. First, I'll show it's in the interval. Then b just a second. So b is the maximum of these, so it's greater than both of these. So b is greater than 7 minus epsilon on 2, which is greater than 7 minus epsilon, and b is less than so if b is 5, then b is less than 7, and if b is equal to 7 minus epsilon on 2, then b is less than 7, and so therefore b is less than 7, which is less than 7 plus epsilon, and therefore b is in this interval. That's beautiful. And then also b is less than 7, which we knew, and b is greater than or equal to 5 because it's the maximum of these two numbers. And so therefore b is in the interval from 5 to 7. And so the interval 7 minus epsilon, 7 plus epsilon is not contained in the outside of this set. And so therefore it's not closed. Right. I'm sure there's an easier way of doing that, to just reason directly with intervals and the sizes of things, but I don't know how to do that yet. I'm sure I could come up with it, but this works. Yeah, my worry was that if my epsilon was too big, yeah. Yeah, I'm so glad that you like that. It was years after I studied real analysis when I realized that the two definitions are actually really similar. And that made me feel better about an interval being both open and closed, because it was, the definitions are actually started to be really similar. And so I go, okay, cool. It's just one's about the inside and the other one's about the outside. Yeah. Are there any others? I'm so glad that was helpful. Yeah. So the only other proofs involving open sets that I can think of other than specific open sets are ones where you prove something like the intersection of two open sets is open, or the union of two closed sets is closed, or something like that. That's something that can be proved, and I don't know if it's the sort of thing that that your lecturer has asked you to do before. Has it been? Okay. Are you feeling okay with how those proofs work? All right, cool. Well, look, thank you so much for coming. I'm glad it was helpful to you. We've only got 10 minutes left. Is there anything you wanted to talk about in that 10 minutes? I'm really glad it cleared some things up for you. What I'm going to do is stop the recording. So thank you everyone who's watching online. I'm going to stop there.